You basically start with the formula. To find the arc length means to write down the formula. Solution. We have 3 formulas. And now your job is just to know which one we need. Cartesian has x and y. Parametric has x and y, but each is a function. In Cartesian, f is a function of x and y. Cartesian x and y both are functions. And polar is theta in r. Polar is the weirdest one from all, so it's easy to detect it. Here it is. It looks weird, so that's polar. Polar arc length formula is L, gigantic square root, integral from alpha to beta. So we have 1 plus derivative squared plus derivative squared, and then original squared and derivative squared. That's the one. Original squared and derivative squared. D theta. We have that. One more thing is, in the whole polar chapter, we gave you 2 formulas. Both are going to the exam. 1 problem per formula. The other one is 1/2 integral from alpha to beta. What was else there? R squared d theta. That's what we did in the previous class. So which one is which? Remember, the second one is area. That's also one thing. I just tried to guess your mistakes on the test. Confusing the formulas is a popular mistake. Area, 1/2 is coming from the sector, formula of the sector. Check out my previous video if you missed the class. Sector gives you this 1/2 r square thingy times d theta. While r squared derivative squared, that's arc length. So write down maybe both, and then you have to actually remember which one do we need for this case. So let's do it. L is alpha is 0, beta is 2 pi, are given the square root, original squared. Well, that's theta squared, and now we're squaring it. That's original. Plus, differentiate theta with respect to theta. Theta squared gives you 2 theta squared. That's derivative squared. So, original squared, derivative squared. D theta. Does it make sense? So arc length actually is the best, always the best thing in all chapters. From Cartesian to parametric and polar, it's always the best formula. Now the problem is to how to integrate that. So let me simplify. It will be integral from 0 to 2 pi, the square root theta to the 4 plus 4 theta to the 4. Right? Yes. D theta.
Squared.
Squared. Why not squared? Yes, exactly. I can see something is wrong. Squared. Thank you. Now I can factor out the theta squared. The square root theta squared plus 4 d theta. Theta squared inside of the square root gives me theta. Remember, theta is a variable, not a constant. Now, so we have theta square root, theta squared plus 4 d theta. This integral is on a test. Guess why? Why this is a good example for the test? Maybe it's a trig substitution. Sometimes we did that. We see when you see a squared and sum, maybe it's arctangent, minus arcsine or arcsecant. What else? Yes? U substitution. Or U substitution. And we also have integration by parts. Definitely not partial fraction decomposition. Numerical is always the last chance. So choose which one, try if it works or not. U substitution is the best one to try. If it doesn't work, move on to something else. But it will work. How do we know? If you choose u squared plus 4, derivative of that is 2, what did I say, u squared? Theta squared plus 4 to be u, then derivative of that is 2 theta, and it's perfect for the u substitution. So this is a good practice before the test. Should I write it down? Let's do it. Let u be theta squared plus 4, then du will be 2 theta d theta. Then you choose what you want. either you solve for what you need, which is this piece, or what I like is multiplying by 2 and dividing by 2. But let's do it this way. Theta d theta is 1/2 du. Plug, this is my u sub. U sub chapter, your favorite one. Plug the first equation and the last equation into the formula. How about the limits of integration? Technically speaking, you're supposed to change them. I will. Actually, they might be better if you change them. Then it will be like no theta anymore. Let's change them. 0 becomes 4. Kind of looks better than theta squared plus 4. If I plug 0, do you know how I'm changing limits of integration? Some people actually keep asking about this, so I think it's not very clear. So theta was 0. U is theta squared plus 4. 0 squared plus 4 gives you 4. Theta was 2 pi. Now u is theta squared plus 4, which is 4 pi squared plus 4. So that will be A and B. New limits of integration. If you know how to keep the previous one correctly, you can do that. From 4 to 4 pi squared plus 4. Now, in yellow, theta d theta is 1/2, let me put it in yellow, 1/2 du. And then the square root has u inside. That was the goal. Because we know how to integrate square root of u. U sub for definite integral. That's what we're just reviewed. So it will be 1/2. U to the 1/2, integrating that gives you 1/2 plus 1 is 3/2. Divided by 3/2. That's multiplying by 2/3, skipping that step. Multiplying by the reciprocal. Bar. You do not go back if you change limits of integration. That was the whole point of doing this work. But you do go back if you did not change limits of integration. You either do one or another one. Don't do both. Make sure you understand what are you plugging in what. U is 4 and 4 pi squared plus 4. But theta is 0 and 2 pi. So it should make sense. Don't plug number of grandmothers into units of money or elephants. It's not the same thing. Units should match. So it makes sense. Now, the answer follows actually. 2 and cancels out 1/3. And we're plugging in and we're getting some kind of not very pleasant numbers, I can see. But who cares? 4 pi plus 4 raised to the 3/2. That can be simplified. Minus 1/3 times 4 raised to the 3/2 also can be simplified. Because 1/2 is a square root of 4 and square root of 4 is 2. So it's 2 cubed, which is 8. So actually the second number is 8. For you to know. Or to be honest, it is 8/3. 1/3 times 8. That is the finite number. That is number of units with 4 pi, let's see, cubed. The pi should be squared. Oh, you're right. Good catch. See this one? I did not see it. It's too small. Squared. That's why I got myself a new computer on Cyber Monday with bigger screen. That's how you know my vision is getting worse. Time to increase the screen size. So, very good. Good catch. That was the arc length for this interesting curve, which is r equals theta squared. Very interesting. Can you try to imagine how r equals theta squared looks like? The bigger the theta, which is the angle, the bigger the radius. And radius is how far I am from the pole. What do you think that can be? Any guesses? I think so, right? Because if something is going away from the center, then it is moving away. And the angle is keep moving. So theta squared. Let's see. And it is beautiful. Look at that. Look at that thing. So when the angle is small, radius is also small. See? So it's keep making infinitely many hearts. And then keep coming back. Very cool spiral. So we found only from one rotation what is the arc length after it finished one rotation from 0 to 2 pi. That's the beautiful idea here. Questions about this? Look at this beautiful thing. Now, I wanted to show you before we move on that since we're on this topic, we're going to do more example right now about area because that's harder. But I wanted to show you that applications of polar equations and coordinates are massive, massive. They're everywhere. Because sines and cosines create circulation or periodic processes, you can draw with sines and cosines everything you want. Your face, that water bottle, that computer. You can describe sounds and even colors, how the color is changing from red to brown. You can describe it all, especially if it's periodic, with sines and cosines. You look skeptical, so I will show you what I mean. Polar curves in Wolfram Alpha. I will show these examples. There are several popular curves, not polar, popular. For example, Einstein curve. Look at that. Look at that, dude. Well, you will be impressed to find out that sines and cosines build all of this, because you can just send these things to keep spinning, and you can abort this spin just like they did here. The spinning started and it aborted it, and then it became a heart. So why not to do it for every shape? You can abort a stretch and shift. You showed this example in pre-calculus class. In calculus 1, we teach transformations of graphs. This is stretch and shift. The number in front of sine gives you different radii, negative, negative, decreasing, shift inside of the function, adding and adding. Now I want to show you that this is just x variable, and this is parametric equation. X depends on t. Look at this thing. This is still x variable, still x variable, still x variable, still. It's still x variable, and now it's y variable. Now there's a y variable, and at some point it ends. It's called a person's curve, Einstein. So that's how you can draw this. And computer does it by itself now, and then gives you the equations. As you can see, it's parametric equations using polar angle and radii. Choose. Choose next one.
Santa.
Santa. Let's do Santa. Look at this dude. Look at that dude. Good choice, because I actually will show you something interesting about Santa as well. Sines and cosine. Look at this. Look at this thing. Include fictional character. Come on.
What is SGN?
So sine. That's a function of sine. There exists a function that defines the sign of the whole thing. So that's what's called SGN. Sine. Sine means negative, positive, I mean. Let me show you the 3D one, Lady Gaga. So first they did it using, so you see how heavy it is? Sometimes internet refuses to show it. In some bad buildings with bad internet, it actually did not show anything. This is using pebbles, pebble stones. That's Lady Gaga, and then this one. And then it's the same thing. Just, so someone had lots of free time and, you know, plus, minus, like, oh, so the nose, minus 39 over 39, maybe let's do 103 over 17. Ah, too much, too big, too small. And that's how you can shrink and stretch things and blah, blah, blah. Finally, they start adding new stuff. Actually, we just learned in my morning class. Look at that, random DC comic. It's always different. So every time I show it, it's different.
Oh, that's kind of cool.
Pretty cool, right? And then there's no equations here, unfortunately. And there's even memes. That's new. Someone edited it like this year, I think. Look at that thing. This is literally what we did today. It's a circle. Come on. This is exactly what we did today. It's a circle. So I assume that's probably like r equals 3 sine theta. And then one more inside of it, and then 2 smaller ones. This one. This one. Very ugly duck. Very ugly duck. Or surreal. Maybe it's modern art. Who am I to judge? This one. This one. Yeah, so they all described how they were done. And finally, American flag. And finally, there are some colored ones. Actually, coloring maps will be your big deal if you stay in STEM, because heat maps are important. We're going to do some of them in Calculus 3 class. Heat maps are important. Coloring is important. Also done with trigonometric functions. So that's a proof for you why it's so important. Annoying, but has thousands of applications. So STEM people have to know this stuff.